Waalaikumsalam, doktor.
Hi, good afternoon. Have you eaten? Have you take your lunch? Not yet? You just wake up, right? Haven't? Okay. It's okay. You can diet, right? All right. We will continue the last week, right? Um, there is a few slide. Okay. Um, so last week I don't know why my internet got a problem. So I hope that for today is maybe okay. We covered for two chapter actually. The last week we see strain gauge, and then after this is piezoelectric. Okay, all right. Strain gauge. Okay, so let's recap back on what we have learned about the strain gauge. So strain gauge, you just need to memorize the formula, right? So what do we have? All right, we have here is a stress. Stress equal to F over A, right? The force. So sometimes the F, we write it is the P symbol. And then we have the strain is delta L over L, right? And then we also have the relationship between stress and strain. So we have the stress here, we have the modulus Young, and then we have the strain. Okay. And then equation 1, 2, and 3 is the basic for strain and stress, right? So right now, when you apply, um, so when you buy the strain gauge, right? So you will have the gauge factor, and then the formula will be delta R over with strain. Okay, so that's it. Formula number 4. And then formula number 5, when we attach our strain gauge on a material, right? For example, you want to build a load cell, so it will give you the other formula, yeah, which is the delta R over R is equal to gauge factor over with modulus Young because you apply it on that material, and over with AB is the area, and you time with the force. Okay, so this is the axial load cell, right? You can pull it or stretch it by uh, horizontal or vertical, right? Axial load cell. And then the last one, we have the bending load cell. So the equation will be, I think we just added blah blah blah. Where is it? Where the bending load cell? Sig x only, right? And AB squared. Okay, sig x. Then you have here is sig x. X that means the location that you put the strain gauge, and then you time with the GF and E, AB squared, and also F. Okay. So equation 5 and 6 is for load cell. So this one we call it bending load cell. Okay. And then when we want to do the measurement, so we normally will apply our strain gauge with a Western bridge. So when you apply the strain gauge with the Western bridge, so the equation for that one, it will be the delta V over V equal to delta R over 4. Okay, so this is the very basic lah. Okay, all right. So this is the formula that we have learned last week. So now let's continue a little bit. Okay, all right. So when we apply the strain gauge with the Western bridge, there are three types. Right? So the first one we call it is quarter bridge. Okay. So the quarter bridge, which is only one active strain gauge that is used for strain measurement. Okay. If you look at here, you apply the strain gauge on the material here, and then you apply the force into this direction, That means this strain gauge is active strain gauge, right? Okay, this is active. Okay, and only one. So when we call it is only one, that means it will be equal to delta V. So this thing we call it quarter, right? Quarter bridge. So I will like delta V to write, I will like it quarter, I write like this, over with V in equal to delta R over R. Sorry, over 4, right? Over 4. I write it again. Delta R over R over 4. Okay? If only one active strain gauge. Okay. And so how about if you have two active strain gauge? So if you look at here, when you apply the force into this direction, and you will see that only this strain gauge is active, and then this strain gauge also active. Okay, all right. And for D1 and D2 is only for dummy strain gauge. Or it's only for temperature compensation. Okay, so remember, right? Okay, so if you have two active strain gauge, so what you will do is you will find the delta V half. Okay, we need to find the delta V. We call it half. Okay, so the formula after this will be equal to 2. Then you time with delta V quarter. That means you need to find the delta V quarter first from this equation. And then for delta V half, you just time by 2 because there is only 2 active strain gauge. Alright. And then the last one, if you have 4 active strain gauge, so if you look at here, when you apply the force into this direction, and this strain gauge also active, right? Active, active, and active. So that means there are 4 active strain gauge. So in order to find the delta V here, right? So I would like to write like this: delta V full is equal to 4 you time with delta V quarter. So the very basic one to find is delta V quarter first. Okay. All right. Any question so far? So far, right? Any question, guys? Okay. Slow down. Because you haven't eaten yet, right? Slow down. No question? Okay, good. So that's the 3 type. Okay. Alright, the rest is about how you're going to install it, blah blah blah, blah blah blah. Okay, this one is used Western bridge, and when we apply this Western bridge, of course, sometimes we need differential, right? We need differential. Okay, compensation gauge. So when the bridge is null, so that means all the resistor will be equal. And when there is two strain gauge, for example, the R3 here and R4, so there will be delta R2, delta R. Okay, so this is how the bridge constant, that what I've been told you before. That means in order to find the delta V half, so you need to time by 2, you time with the delta V quarter. So it is like A equal to KB. That means the bridge actual output, for example, the delta V half, alright, only 2 active strain gauge. So you just need to time with the 2. That means K depending on how many active strain gauge. So that means 2 you time with delta V quarter. Something like that lah. So that means this one, this A, you want to find the actual, and you just time K time with B. Okay. Right. Okay, so this is what I mentioned before. For quarter, this is the formula. For half, this is the formula. And for the full, this is the formula. Okay. So in a question, so you need to define, you need to check it whether what we call it, whether the bridge is a quarter or full and so on. Okay. All right. So let's look example 15.4. Okay, 15.4. All right. An axial load, an axial load is applied to a connector. The change in strain is measured by applying force strain gauge as shown in figure below. Okay, he applied the force strain gauge, right? But we need to know which one is active, which one is dummy. Okay, two strain gauge are used for strain measurement. Okay, only two. Right, the word is only two, right? Only two strain gauge. That means only two strain gauge that is active, right? While the other two is for the dummy strain gauge, okay, for temperature compensation. All right, so we know that this strain gauge is attached to the western bridge. So that means you want to find the delta V half is we equal to 2 we time with the delta V quarter. Okay, this is the first one. Okay, and then it said that if the maximum force applied is 400 Newton, gauge factor equal to 2.2, modulus Young equal to 69 gigapascal, and current flow is 25 milliamp. Determine the maximum output. Okay, this load cell can be measured. So maximum output, that means the delta V half lah, right? Delta V half. So the question. Okay. Alright. The resistor gauge 120 ohm. Okay, all in 120 ohm. So this is the axial load cell. So what is the formula that we can get it? This one, right? Before that, delta V quarter. So we can get it delta V quarter over with V in is equal to delta R over 4. Okay, and then we can get it the formula for the load cell, delta R over R equal to gauge factor over with modulus Young, and then you time with AB, you time with the force. Okay, all right, so we already get this one. So the concept is in order to find the delta V half, so we need to find the delta V quarter. In order to find the delta V quarter, so we need to find the delta R over R. In order to find the delta R over R, so we can find all these things. But in this question, it doesn't give you the V in, right? So the V in you can find it by look at the current. Okay, so because the V in, so it can be V equal to IR. We will look into that. Okay, right. So that is the step lah, right? To find this, and to find this, then you can get delta V half. Okay, all right. Any question? Any questions so far? No.
No, Doctor.
Okay, everything clear, right? Right. So let's find further delta V. Delta V over R is equal to K factor over with modulus Young AB you time with the F. Okay. So K factor it gives you 2.2. Modulus Young 69 giga, right? Giga and power of 9. 1 millimeter times 1 centimeter. 1 millimeter, that means 0. Isn't it? So you just times 1 centimeter, that means 0.01. Then this one is force 400 Newton. Okay. Alright, can somebody calculate it for me? How much is it? Okay, Ervin Ng, thank you. 1.27 times 10 power of minus 3. Okay, this is all right. And we already got delta R over R. After this, we're going to find the delta V quarter. But before that, let's find the V in first. Okay. So in order to find the V in, we can draw again the western bridge. Okay. And so this is the western bridge that contains the four resistor, right? Which is the two strain gauge, actually the four strain gauge, right? It said that the current flow is 25 milliamp. Okay, that says all is 120, right? All 120, 120, 120. So the current flow, that's mean the current flow to here is equal to 25 milliamp. So we're going to find the V in here. Okay, so you can find the V in by apply the formula V equal to IR, right? So V in equal to IR. So I is 25 milliamp. But for R, you need to add it, what? 120, 120. Okay, this one, how much? 240 times 25. Where is my calculator? That's why you got it 3.1, right? 3.1 or something like that. So 2 you times with 1.905 times 10 power of minus 3. What is it? 1.9, okay. Alvin. Okay, 3.81 times 10 power of 3. All right, so that's it. I hope it's very, very clear for you. Okay, find this one first and find the V in. Oh, I forgot to record. Good luck. What is it? Okay. Okay. Then number 3, find this one, and number 4, you can find data we have. Okay. Everything clear? Any question? Simple, right? For the strain gauge is a very, very simple. Okay. All right, no more questions. So let's proceed for the next slide. Okay, example 15.5. Okay. Strain gauge are arranged as in figure below. The value for resistor R1 equal to R2 equal to R3 and equal to R4 is 120 ohm. And the V equal to 9 volt. So V, if you look at here, is V here, right? Okay. If the output from the bridge equal to 20 millivolt, calculate the force applied. Okay. So if you look at this one, when you apply all the strain gauge like this one, right? So when you apply the force to this direction, you will see that all the strain gauge is active, right? Will be active. So there is no dummy strain gauge in this case. So that's mean the delta V for these cases, that's mean is the delta V full. Okay, it's a full bridge. So delta V full, okay, it shows that the output of the bridge equal to 20 millivolt. So that's mean the delta V full equal to 20 millivolt. Okay, so the formula for delta V full is equal to 4 delta V quarter. Alright, so that's it. So the question asks you to calculate the force applied. Okay, so from this one we can know that delta V quarter over with the V in. So V in it give it to you 9 volt. So equal to delta R over 4. Okay, done. So because this one is the bending load cell, so we can have the formula for bending load cell equal to what? 6x time with the gauge factor over with modulus Young, AB squared, and then you time with force. Right. So the question asks you to find this guy, force, right? Maybe force be with you, right? May the force be with you, right? The question asks you to find the force. Hey, find this guy, force. So the step is quite simple. The first one, we can find the delta V quarters first. Okay, delta V quarters. So from delta V quarter, you can get it the delta R over R, done. And then from delta R over R, you can get it force, done. Because gauge factor is give it to you, okay. Gauge factor this one, right? Factor tolok, right? GF, okay, equal to 2.4. And B for the length, for the width, also given to you, A and B. And X is where the location that you apply the, what we call it, the modulus Young, the strain gauge, right? X, 50 milliamp. How about L? L and T, B equal to A, L and T. Okay, all right. So all given to you here. Yeah, there is step here. So the first one is to find the delta V quarter. So that means you need to divide with 4, right? So you need to divide with 4, delta V quarters. Okay, done. We can find it. So when we get the delta V quarter, so we can find the delta R over R here. So we can get this guy, done. And then from this guy we can get it the force, all right, or P Newton. Okay, it's a simple step, right? A very, very simple step, isn't it? Yeah. Okay, good. Any question for this one? Any question? Okay, slow down. Right, slow down. No. Okay, And the rest is about the summary, okay, about what we have learned in this topic. So this is the formula, right? Formula involved. And this one you need to differentiate. Which one is full, which one is half, which one is the quarter. Okay. So there is 9 formula that you need to memorize. Okay. Done. For based on that formula. Okay, the application about the strain gauge, it also can measure the cent of torque. All right. So when you put it strain gauge like here, and then this is the material that you want to measure, so you also can do that. Okay. All right. So that's it for this topic. So let's take a break for 2 minutes, and then we continue for the next topic. Is it okay, guys? If okay, please type okay. All right. Let's take a break for 2 minutes. Only 2 minutes, right? Okay. So the next topic will be a transducer. Okay. For your test two, so the topic that will be covered only until the strain gauge, right? So you have learned about the filter. Okay. So what's else? You have learned about Western bridge, and then you have learned about the strain gauge. Okay. And yeah, before that you have learned about the RTD, thermistor, right, capacitor transducer, and thermocouple. So filter, RTD, thermistor, thermocouple, and also the strain gauge. So that's why will be asked during your test two. Okay. So the rest for this topic like piezoelectric and also capacitor, capacity transducer, it will be and your assignment. Okay. All right. Okay. So let's go through for topic piezoelectric. Okay. Piezoelectric transducer is a good thing about this transducer is it can react as a sensor, right? And also it can react as the actuator. Okay, let's look about it. So this what we call it, the material, right, had been covered in 1818, right, by this guy, Pierre Curie, I don't know, in quartz crystal. So he found it. Okay. So what it do is, piezo that's mean in term of the Greek word we call it piezing. That's mean to press. So what you do is when you give some force, right, to here, okay, it will generate the electric force, right? Electric magnetic force. Okay, so that means, of course, if you have the material here, if you put it in the multimeter, right? So you will see that you will get it current flow through this. Okay, so that's what we call it piezo. You press it, you can get the current, right? Or you also can give the voltage, and then you will see the deformation of the piezoelectric material. Okay, so the effect that is explained by the displacement of ion in crystal. Okay, this is the ion is moving and so on when you give some force, right? So when the ion is moving, then that means it will generate some electrical. Okay, all right. So this is in terms of theoretical, right? So type of the effect, when you apply the force into this direction, so it will give you what we call it the voltage. Okay, so when you apply the force into this direction, it also gives you some voltage here. And also if you have give the voltage into that piezo, it can deform, whether it can extend or it can compress it. Okay, so how can we use the piezoelectric as the displacement sensor? So it can give it to you like this. So piezoelectric, it can be like a strip, right? It's a strip here. So when you apply the force into this direction, so you can measure the voltage that had been produced. Okay, so the displacement will be high, so the force also will be high. So K is the constant for the crystal, for that material. So this is the very basic about the piezo strip. And the application of the piezoelectric as a sensor, okay, is given to you like this one. So let's say this is the piezoelectric material. Okay, so it can be used as the force sensor. So when you have some force onto this direction, so this piezoelectric material, the ion will be move around, and then it will generate some voltage here, delta P. Okay, so when this housing, right, is vibrate, right, it will push the piezoelectric, okay, and then it will give some voltage. Okay, so something about the pressure sensor. Okay, so you will give some pressure, right, the above the housing, right, whether in terms of the gases, for instance, or the liquid and so on. So it also will produce the voltage here. Okay, something like that. And it also can be used as the accelerometer that can move into the x and y direction and so on. So where you put some mass, right, on the top of the piezo, and then when the force, right, will be applied to here, that means the mass will push the piezoelectric, and then it will produce the voltage delta V. Okay, all right. So this is the application of the piezoelectric itself, and the information about the crystal, right? So it's given to you like this one, the Q, K equal to Kx, the displacement, K is the stiffness of the material. So what is the Q is the net charge, right? So you want to go to detail, right? So you got it, this one. And also this example of the piezoelectric. Okay, so where you can have the relationship between the Q charge and also the capacitance itself. So this is given the QC CV, but this one, it doesn't matter lah. It's never going to be asked for this subject, right? So the behavior of the quartz crystal or piezoelectric is given to here, right? So the temperature, it can rise up, it can maintain to 930 Farad, 30 Fahrenheit, and then the maximum stress or pressure, it can handle up to 20 psi. Okay, so let's look about the application. So let's say you have the combustion monitoring. So when you can put the piezo here, right? Okay, in order to know, okay, so when this one conversion will move in, move out, okay, go up and down, so you can measure the output from here, from the piezo itself. Okay, all right. So pros and cons. So this is the pro and con about this sensor. Okay, all right. The more important thing about the direct and converse piezoelectric effect. Okay, this is how I have been told you before. That's mean the piezo itself, it can react as the sensor, or it also can react as the actuator. Okay, let's look. Okay, there is two type which we call it directly effect. That's mean when the piezoelectric crystal is experience tension, or electrical potential is generated. That's mean the first effect, when you give the force, external force, to that generate the electromagnetic force, okay, delta V. All right. So when you give this one the tension, right? So this one is compressed. When you give the tension, that means it will give you the voltage, but in terms of the inverse direction. Okay, this is the first effect. The second effect, we call it conversely. Conversely, that's mean when you apply the voltage, right? The voltage to that piezo, that's mean it will deform that material. Okay, it will deform. That's mean it will extend. Okay, tension, this one. And if you give the voltage into reverse polarity, so that means it will compress. Okay, so that means this one, it can react at the actuator. So this one, it can react at the sensor. Okay, this is the good thing about the piezoelectric. Okay, my question is, by knowing this effect, can you tell me the application of this piezoelectric? Where is the application for this one? Beside this one, beside the conversion monitoring application, what the simplest application that you have seen right now about the piezoelectric? Where is it? And it's happening now. Where you can get the piezoelectric uh, material? Where is it? Come on, guys, please type in the chat. The simple application is happening now. The simple application, where you can get it? Do do do? No, except the force sensor and so on. Okay, where is happening now? Guys, are you still there? Okay, so the simple application is what? Is the microphone and speaker, isn't it? Is it correct? So, wow. Yeah, inside the microphone, it have a piezoelectric material. Okay, inside the speaker, it also have the piezoelectric material. Okay, so the microphone right now, it use this effect directly, right? Microphone, that's mean this one for microphone. That's mean when you talk, your audio will give you the force into the microphone. So the microphone have a piezoelectric material, and then it will convert it into the voltage, and then that voltage will be amplified and then will be converted into the audio again. Okay, so um, from that one, the second effect is for speaker, right? Yes, mean when from the computer it will generate the audio, right? The sound. That's mean it will do some current to amplify, and then it will go to the piezoelectric material, and then the piezo will be extend doom, and then we compress doom, 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 doom. Okay, like that. Okay. So the simple example is like microphone and also speaker. Okay. we look at the example. This one is described back on what we mean by directly and also the conversely. Okay. All right, so this is what I told you. The piezoelectric itself is a special about it. It can be like actuator and also sensor. Okay. All right, the rest is about the piezoelectric application. It can be used as accelerometer, right? That has been told you before, and it can also be a piezoelectric motor, right? That can vibrate, right, and so on. And it also can be used to measure the vibration, okay, for the piezoelectric drill and so on. Okay, so let me share you a little bit about what you can do when you have the piezoelectric transducer. Okay, because the piezoelectric, it can generate a voltage, right? So yeah, the second application is like the buzzer. Inside the buzzer have the piezoelectric material like this. Okay. So this is the example on how they build a very basic application like this one, right? Okay. Yeah, it's a simple one. So when you want to build the sensor, right? Yeah. Now you can see the LED right now. Yeah. What you do is charging the capacitor, and then after that it will switch on the switch, so you can get the LED. Now, because the concept of the capacitor is it can store the energy, right? So it is the piezo material. Okay, you also can build like you have a multiple piezo transducer, and then you can build it for charging your phone, right? You can put it into the shoes. Okay, this is the application, right? The simple application. It can be like energy harvesting actually. We put it forward, right? Okay, this is the concept when your pick, we put it in this one, okay? And then the power bank, wow. So let's see whether it's work or not. Okay, you can put the battery here to charge your battery, right? But that one for only one cell of battery. Okay, so right now 3.5. For initial one, 3.5 volt. So let's look whether it work or not. Is it funny, guys? Okay, now you walk, okay, and then you run, then you walk, okay. It's a good thing, right? 23,000 of you. Wow. So let's look. Before this is 3.5, right? Wow, 3.9. It's work, guys. Okay, but this one is only for three piezo, right? So you can put multiple piezo. So anything that involving in term of the vibration, you can do that. Okay. So we thought that it's only for the just to play around what, but this company have proof is right, have deployed it in the real world. Okay. Yeah. This is yeah. Yeah, the good thing about the piezo transducer, that's mean it can do the what we call it, the energy harvesting, right? So that's mean when you step on that one, right, and then there will be the piezo here, okay, this one. So you can generate an electricity, right? Maybe you can power on the light, right, on that city. Okay. Um, mm. So last time I'm going to do some research, right? So I'm going to put the piezoelectric transducer into a treadmill. Okay. So when we do some jogging on the treadmill, and then we can get the energy back from the treadmill, right? Yeah, because the treadmill will be vibrate. Okay. We can apply the piezo at that one. Or maybe you can apply the piezo itself on the air conditioning compressor. So if you look at in uh, UTM, there are a lot of the compressor, right? The air conditioning, the air conditioning compressor, right? So when you touch it, the air conditioning uh, compressor, you will see some vibration, right? So if you have a lot of the piezoelectric transducer, you apply on that one, so you also can get some energy from there. And then from that energy, you can power on some light. I don't know, so it can what we call it, can save the energy, right? For honesty. So that's it, right? About the piezo. Anything, yeah. You can combine with this for detect the raining. Okay, anything can do the vibration, you can do that. That's it for today. Okay, so for the piezoelectric, actually there is no calculation about it. It's just for your assignment. And I think that's it for the next week. We have one more topic, which is the capacity transducer, and then we will discuss a little bit about your project so far. Okay. By this Sunday we don't have class because I have another class, right, on the morning. So please spend that time to do your project. Okay. Uh, guys. So right now, how about your project right now? Is it okay? KO. Not doing yet. Okay.
So far so good, Doctor.
So far so good. Okay. Right. If you have any question regarding your project, you can ask me. Still in progress. Good, good, good. LGT put as slow. Okay. So the due date will be uh, until of the what we call it, until of the uh, your end of your study week. Okay. What Afiq asked for the sample report. Okay, I will upload it in the e-learning. Sorry, Afiq. So you have WhatsApp me before, but I forgot it to reply. Okay, I will put it in the e-learning. Okay, the sample report. All right. So I think that's it. Okay. Before that, so maybe today or tomorrow I will share you the mark for the test one. Okay, right? So you can look at your mark because yeah, because the lecturer have finished it to mark so his question. So now I'm waiting for him, and then he have done it. So I will share to you by today or maybe tomorrow. Okay. All right. So that's it, guys. Thank you for your attendance. I will see you again on next Thursday. Okay. All right. Tap, tap, tap. All right. Thanks. Bye.
Thank you, Doctor.